Good morning all. Hope you all are fine. Before we start our lesson today, there is one appeal. Only 7 or 8 people are watching the videos every day. I can see on YouTube. It's not fair. We are taking so many efforts for you people and you people are not responding to it. If you do not understand anything, you can ask 10 times. But please do watch it. Okay? Now, let us continue with the same topic, that is semiconductors. Last time we have seen the pure or eccentric semiconductors. Now let us see impure or extrinsic semiconductors. First of all, what is meant by impurity? See, scientifically impurity does not mean something bad, but it means that there are more than one type of atoms present in the same place. Okay. So whenever a trivalent or pentavalent atom is added to the silicon crystal or the germanium crystal, then such semiconductors are called as the impure semiconductors. So this process of adding the trivalent or pentavalent atom or impurity to silicon or germanium crystal is called as doping. Okay, and the trivalent or pentavalent atom which are added over here, for example, we can add the atoms like boron or aluminium, okay, which are trivalent. Okay, then and we can add or we can add phosphorus, which is pentavalent. So these impurities which we are adding over here, either trivalent or pentavalent, they are called as the dopants. Okay, and here there are two types of dopants, one is trivalent and one is pentavalent. Okay, what effect they will produce we will see in the later part. Then here whatever the semiconductor is formed after addition of the impurities to the silicon or germanium crystal, okay, such semiconductors are called as impure semiconductor or extrinsic semiconductors. Types of extrinsic semiconductors. Here there are two types of extrinsic semiconductors. One is p-type extrinsic semiconductor and the second one is n-type extrinsic semiconductor. Here P stands for positive and N stands for negative. But actually they are not positive or negative. But the charge carriers in this type of conductors are either positive, that is holes, or negative, that is electrons. That's why they got the names like p-type semiconductor and n-type semiconductors. So first let us see what is a p-type semiconductor. When a trivalent impurity is added to silicon or germanium, then the 3 atoms of the trivalent impurity will form 3 bonds with the 3 silicon atoms in the neighborhood, and there will be one deficiency left behind which is called as the hole, and this deficiency or the hole left behind acts as the positive charge carrier, and because of this it is called as the p-type semiconductors. Let us see in detail what is a p-type semiconductor. Okay, let us suppose that there is a silicon crystal, and in this silicon crystal, okay, we have added a boron atom as a trivalent impurity. This boron atom has, which is trivalent, has 3 electrons in the outermost shell, and hence it is trivalent and capable of forming 3 bonds with the 3 neighboring silicon atoms. And as it has only 3 electrons in the 3 outermost shell and can form only 3 bonds, then we will find that it has a deficiency of 1 electron which acts as a hole. Okay, so here this is hole. Okay, just check it out. I'll make it with the red pen so that you can understand. So here is one hole present. Now suppose because of the thermal agitation, that is because of the rise in temperature, some of the bond breaks over here. Suppose this bond breaks over here. So when this bond will break, 2 electrons present in this bond will come out. Suppose these 2 electrons are gone to 2 other silicon atoms. One is here, one is here. Then because of the loss of these 2 electrons from this bond, then these 2 silicon atoms will acquire 2 holes. And now you can see that here in this crystal now there are 2 electrons, that is there are 2 negative charge carriers. Okay, and there are 3 holes, that is 3 positive charge carriers. Okay, as the number of electrons in this are, okay, less than the number of holes. Okay, that is the positive charge carriers are in majority. Positive charge carriers are in majority. So, because of this majority of positive charge carrier, such type of extrinsic semiconductor or impure semiconductor is called as p-type semiconductor, because it has more number of holes as compared to more number of electrons. So when such type of conductor will be connected in the circuit, then these electrons will flow in the direction opposite to the direction of the applied electric field, and these holes, they will move in the direction of the applied electric field. Remember, here holes are moving does not mean that practically the holes will shift from one place to another place. What happens is that the electrons from some other atoms will come to these holes, and holes will be created in place of those electrons from where these electrons are coming and filling these holes, and in this way these holes will be shifted to that place. And in this way we will find that when a p-type semiconductor is connected in the circuit, then here the current is flowing because of both the charge carriers, that is electron as well as hole. But over here the majority of the charge carrier is positive, that's why it is called as p-type semiconductor. Here we can see that because of being trivalent, then this boron atom has the capacity to accept the electron. That is why boron is called as the acceptor impurity. Okay, and this acceptor impurity will have a separate energy level for the electrons, which is called as the acceptor energy level. Let us see in detail what is the acceptor energy level. The energy band diagram of the p-type semiconductor is as follows. Here, this is the valence energy band, and this is the conduction energy band. Okay, then so conduction band will always have the electrons which will have high amount of energy, and the valence band will have the holes which will have the lesser amount of energy. And we must remember that whenever the impurities are added, after that a special band will be formed, or a special energy level will be formed, which is called as the acceptor energy level. Remember, this is the acceptor energy level. Okay, acceptor energy level is just above the valence band. It is just above the valence band. Remember, whatever the acceptor energy level will be formed over here, then which will be accepting the electron from the other atoms, then that acceptor energy level will be just above the valence band. Okay. The second type of extrinsic semiconductor or the impure semiconductor is n-type semiconductor. When a pure semiconductor like silicon or germanium is doped with the pentavalent impurities like phosphorus, then it has electron as the majority of the charge carriers and holes as the minority of the charge carriers. And as the electrons are majority charge carriers which are negative, that is why it got the name n-type semiconductors. Let us see how the n-type semiconductors are formed. Just assume that as what we have seen in the previous case, here there is a silicon crystal. In this silicon crystal we have added a pentavalent impurity like phosphorus. Now when you will add the phosphorus over here, phosphorus being pentavalent will form 4 bonds with the 4 silicon atoms in the neighborhood, but there will be no atoms left in the neighborhood to form the 5th bond. And because of this, okay, each phosphorus atom will be left with 1 extra electron. It will be left with 1 extra electron in it. Okay. Now suppose because of the thermal agitation, any of the bond breaks. Suppose here this bond breaks, then when this bond will break, the 2 electrons present in this bond will get shifted to some other atoms in the crystal or in the semiconductor, and 2 holes will be generated in place of those 2 electrons. Now you can see that here there are 2 holes and 3 electrons. So we can easily understand that the negative charge carriers, that is number of electrons, are more than the number of holes. Okay, as the number of negative charge carriers are greater than in number than the positive charge carrier. Because of this reason, such type of semiconductor is called as n-type semiconductor, because here the majority of the charge carriers, that is the electrons, are in majority. Okay, and now when a pentavalent atom will be added over here, then this pentavalent atom gives one extra electron to the n-type semiconductor. That is why here the phosphorus is called as donor impurity. Remember, in the previous case, boron was called as the acceptor impurity because it was having an excess of hole and it was accepting the electrons. Here, the phosphorus, which has the extra electron, is donating the electron to the semiconductor. That is why it is called as the donor impurity. And because of this donor impurity, there will be a donor energy level also. Let us see what is a donor energy level and where does it exist. So here is the energy band diagram of n-type semiconductor. As usual, this is the energy band of the conduction band, energy level, energy of the conduction band, and this is the energy level of the valence band. And when the new level will be formed for the donor, so that donor energy level, okay, that exists just below the conduction band. Remember, this is the donor energy level. Okay, previously we saw the acceptor energy level. Acceptor energy level was just above the valence band and the donor energy level is just below the conduction band. See, it is important to remember this, that the acceptor energy level is just above the valence band and the donor energy level is just below the conduction band, because in the last part of this chapter when we study the LEDs, that is light emitting diodes, at that time we need the knowledge about this. Okay, when it will come, I will be explaining you then. Now let us see what is a p-n junction diode. Okay, see, diode, di stands for 2 and ODE stands for the electrodes. Means it has two terminals, that is positive and negative. Okay, like what we have cathode and anode in a cell. The same way here we have the diode. Okay, it is p-n junction diode. So two things are clear over here. First of all, it has two ends or two electrodes, that is and it is p-n junction. So one end is p, one is n, and junction means what happen here, the p and n type semiconductors are joined together. Then when a piece of silicon or germanium is doped in such a way that half of it is doped with the pentavalent impurity to form n-type semiconductor and half of it is doped with the trivalent impurity to form the p-type semiconductor, then such type of semiconducting device is called as p-n junction diode. So here, if you look at the diagram, then half of it is doped with the p-type impurity, acceptor impurity, that is trivalent, and hence it will have the majority of the holes in it. On the other hand, the n-type semiconductor is doped with the pentavalent and it will have majority of the electron in it. That's why it is n-type semiconductor. Now, the moment this junction is formed, then what happens here is that the first layer of the here acceptor atoms. Now, let us see at the symbols used over here. This circle with negative is the fixed acceptor atom. Okay, which will be present in the p-type. Whenever electron will come to it, it will accept it. On the other hand, in n-type there is a circle with plus sign, which is the fixed donor atom. Then it will keep donating the electrons. Then here positive signs are the movable holes and negative signs are the movable electrons. So the moment junction is formed, then on the right side of the junction, whatever the atoms are there, they have the extra electrons because they are the donor atoms. On the other hand, on the left hand side, the first layer of the atoms will have the plus sign on them because they are the acceptor atoms and they are the holes with them. So the moment junction is formed, then these holes from the n-type semiconductor move to the p-type semiconductor as the electron and hole get recombined over here. See, when a hole will be filled with the electrons, then it is called as the recombination. The moment recombination will take place, then these atoms over here in the neighborhood of the junction will lose their electrons. Okay, and form a layer of atoms with the positive charges over there. Okay. On the other hand, the first layer of the atom or the atoms in the neighborhood of the junction on p type will accept the electron from the atoms of the n side, and hence they will become negatively charged because their holes are neutralized by the electrons from the n type. And in this way, what will happen? Near the junction, then two levels will be formed. In the n-type semiconductor, there will be a layer of atoms which will have deficiency of electrons, and on the p side, there will be a layer of the atoms which will have the deficiency of the holes. Okay, so we say that in this region here in n side, then electrons are depleted, and on the p side the holes are depleted, and that is why this layer formed over here, okay, is called as the depletion layer. It is called as the depletion layer. Depletion layer. Okay, see, when this depletion layer is formed, okay, after the formation of the depletion layer, see, if suppose more electron wants to come to p type, then these negative atoms which are present on the p side, okay, repel the electrons back to n side. Similarly, if the holes want to shift over here, then these positively charged atom on the n side will repel them back, and in this way what will happen? Then the moment depletion layer is formed, then the flow of the charges across the junction stops. Okay, but what happens here is that on the n side, then all positive hole get accumulated. Okay, on the n side, the negative electrons get accumulated, and because of this accumulation of the charges near the junction, then the layer of the holes on the n side starts behaving as the positive terminal, and the layer of the electrons on the p side starts behaving as the negative terminal, and this depletion layer starts behaving like a fictitious battery. It starts behaving like a fictitious battery. Fictitious means imaginary battery. Okay, fictitious battery or cell. Okay, then now whatever the depletion layer is formed over here, which is behaving like a battery because of the accumulation of the charges on the two sides, that is the fictitious battery, then that does not allow the movement of the charges on the either side, and hence it is said to be creating a barrier, and that's why it is called as the potential barrier. We call it as the potential barrier. Okay, and so long as this potential barrier exists, then no flow of charges is possible. No flow of charges is possible, and because of this, then the flow will stop over here and the depletion layer will become stable. Today we will stop over here, and tomorrow we will see in detail what is the depletion layer and what is the importance of the depletion layer, and what is the potential barrier and how can we decrease the potential barrier. Okay, stay at home, stay safe. Thank you very much.